Today we'll take a look at how to do conic sections in polar form. You might have done this before, but we'll review that idea of a conic section and we'll apply it to the polar form using r's and thetas. We'll describe eccentricity and directrix for all of those types of things. And we'll do a bit of calculus too. We'll look at the derivative dy dx for those particular types of functions. So again, this is kind of nice, right? We can, as you've seen, conic sections, ellipses, hyperbolas, and parabolas all have very, at least somewhat different equations that we use to generate them in rectangular coordinates. But assuming we can translate or shift those curves to fit one focus point on the origin, we can actually use the same generic polar equation for all three of those conic sections, which is pretty cool. Again, so we're assuming that there is a focus on the origin, and we'll write an equation for a line called the directrix that helps us guide that polar curve. And we use those two things in order to generate the equation. And the basic form looks like this. Notice this could vary depending on whether you're using a sine or a cosine function, and you might see a plus or a minus in that denominator between the two terms. But r equals ed divided by 1, always 1 specifically, plus or minus e times either sine or cosine theta. Those formulas will sort of create a polar conic section. And how do we tell which one? Well, we use this eccentricity value e to determine that. Specifically, if we get an e value between 0 and 1, we have an ellipse. If we get an e value equal to 1, we have a parabola, and if e is greater than 1, then there is a hyperbola instead. We won't go into too much detail about what this eccentricity number means, but it's a ratio of measurements between the focus to the curve and the directrix to the curve. The directrix being a line that we use to define that eccentricity, and it's determined by the value of d in the formula above, whether you're using a plus or minus, and whether you're using a sine or a cosine. So these four examples of curves are pretty good ones to get a feel for which formula to use when. Right? If your curve is opening left or right, then we're going to use a cosine function. That shouldn't be surprising. If the curve opens to the left, in other words, the directrix is on the right side, then we use a plus in the formula. If the curve is opens to the right, so the directrix is on the left, then we use a minus there. A way to remember that is that if those directrix lines are located to the left or below, in the case of the sine function, we end up with a negative number for our line, our directrix line equation. And so that corresponds to the negative in our formula. Let's take a look at a few, and I think you'll get a good feel for how that works. You should be able to, looking at a polar function in a conic in polar form like this one, you should be able to determine those different parts that we talked about. For part A, this is pretty easy because we've got a 1 already built into our function here. Remember, this numerator, this 2, is like e times d, and this 2 in the denominator represents the e value, since we've got a 1 already built in. So we can pretty quickly determine from part A that e has to be 2, which means the graph is going to take the shape of a hyperbola here. For the directrix line, we need to calculate that d value, and that's where, once you've determined e, the numerator comes into play. Right? If ed is equal to 2, and we know e is equal to 2, we can divide 2 by 2, and we'll get a d value of 1. And so that means, since there's a plus built into the formula down here, right, that means that we've got a directrix equation of y equals positive 1. Excuse me. So a sketch, we've got a horizontal line, y equals 1, as the directrix. Remember, we've got a focus at the origin. We know the hyperbola is going to curve between those two things. And since it's a hyperbola, we know that there's going to be another piece that curves up this way. For part B, notice that's a little different. We need to simplify or rewrite this one into its standard form by dividing that denominator by 3. In other words, also dividing the numerator by 3. Right, so this one would become 8/3 on top. On the bottom, we'd have 1 plus cosine theta at that point. And so you can see that the eccentricity is just going to be 1 from the denominator there, which means that we have a parabola shape to work with. And we can calculate that d value to be 8/3. So we know that x is going to be positive 8/3. That will be the location of the directrix for this one, which represents a vertical line. And so since we've got a focus at the origin and a directrix as a vertical line in the positive right direction, x equals positive 8/3, we know the parabola will curve between those two things. Lastly, for part C, we again need to do a little bit of work to get that written into its standard form. But we would divide the top and bottom by 3 again, which means that the coefficient of sine is going to become 1/3, indicating an ellipse shape. As far as the directrix goes, we'd end up with the numerator being 5 here, but then that means that the directrix would represent, again, here in this original one, you could think of this as a 1 and a 5 times a 1, right? But we end up with a directrix of, in this case, -5. Negative coming from the negative sign in the denominator there. So our linear equation, y equals -5, represents the directrix. And for an ellipse, we know that's going to generate a shape just like this. Right? We've got a focus, we've got a directrix down here, so there's an ellipse shape that comes in between here. I wouldn't stress out too much about making really good detailed sketches just based on these graphs and based on what we just did. A great idea in order to practice getting a feel for where exactly some points on these curves will be is to just substitute in some values of theta, specifically those ones that, that separate the quadrants. So 0, pi over 2, pi, 3 pi over 2. You should double check for these graphs. You should plug in those angles into these 3 equations and see what the corresponding radii come out to be, and practice plotting those polar points. And you'll see that the graph does cross through all those points for each of those. So I recommend experimenting with that if you've got time. Let's take a look at one last example, and this one's already kind of worked out for us. But suppose we want to find the derivative dy dx, the slope of a polar curve. We can do it that same way that we talked about before. We'll use dr d theta sine theta plus r cosine theta divided by dr d theta cosine theta minus r sine theta. And we did that in the polar calculus section. But we'll use that formula in this particular case to find out the slope. As you can see, this gets pretty messy. Right? Our r value, if we rewrite with a negative exponent, our r function looks like this. So we plug that in to these two spots. And we can find the derivative using the power rule combined with the chain rule, and it looks something like that. We'd end up with -2 times 2 cosine theta over the original 1 plus 2 sine theta squared. Plug that into those two places for dr d theta, and we've got a massive slope function. This is the slope of that polar curve in terms of theta, but the rectangular slope dy dx. You could apply that to find the slope at a certain point, or even write the equation of a tangent line, just as we did in the previous section.